he's the founding chair of the Michigan Robotics Undergraduate Program. And he's also currently serving as the Vice President of Educational Activities for IEEE Robotics and Automation Society. So we're therefore very delighted to have Professor Jenkins here, and the topic is also on education in robotics. So Chad, the floor is yours.
All right, thank you so much. Thank you for having me here. It's great, thanks for coming out so early in the morning. That's really appreciated. And you know, it's also a big thrill for me too, because we're running the AAAI conference. It's the largest conference on artificial intelligence ever in history, depending on how you count. Maybe by a number of attendees, maybe, but definitely by numbers of submissions. And so it was good to get away from the conference for a little bit, to come here and talk early in the morning, especially as we have a lot of deadlines right now. So it's really great to be here. Thank you, Rajat, for that great introduction. And so one of the things that, you know, this is a little bit of a new talk formulation for me, because I'm always trying to balance all the things that we're doing in education, because I think really robotics is meant to be an academic discipline. That's where we are right now. And so the undergraduate program, the degree programs, really are the things that help you decide what is a roboticist. It's the intellectual organization of your discipline. And that intellectual organization also allows you to extend to new ideas and that research. And so we're seeing this right now with humanoids. Imagine it's not just one humanoid, but multiple humanoids, drones, all sorts of heterogeneous robots working together. And in order to realize that vision, we have to both think about education and how we do advancements in research together. And that's what makes higher education special. And so just to give a sense of one of the robots that we've worked with, so this is the Agility Robotics Digit. This is a robot that my colleague Jesse Grizzle had in the lab. And I've had the good fortune to work with him. So one of my students and some of his students work together on getting this robot to be able to do various tasks at the building scale. So being able to pick up objects and take them to places that are beyond just the lab, but work in common human environments. And this really poses new, interesting, and challenging problems for us. I've had the good fortune of also working with a number of mobile manipulation platforms. Our still go-to is the Fetch robot right here, so capable of mobility and manipulation. We've had this robot since 2015 when I started at Michigan. So somehow we've been able to keep this robot alive and working over 10 years. But the ability to have dexterity in complex cluttered scenes that are like our human environments is really one of the things that is one of the major challenges that we're starting to be able to address in robotics. One of the things that got me to come to Michigan in the first place was I saw this great video from Ryan Eustace. Ed Olson came and showed me this video, and this is the ability to do mapping at the large scale. So this was from their autonomous car. They were able to build fabulous 3D models of space. So that's Ann Arbor right there. You can see the football stadium, downtown Ann Arbor. In blue, you're seeing what the robot has already mapped out. And what you're seeing in red is what the robot is what the car is seeing currently. And so this sort of gets to the state of where robotics was. This was cutting edge as of 10 years ago, 15 years ago. But now it's commonplace, it's state of the art. But now the robot needs to understand the semantics of our scene. They need to understand that that's not just points, but those are bicyclists going through the middle of the intersection, the trees, the cars. It's not just building geometry, it's about understanding the semantics of our environment. And so a lot of what we're doing in robotics right now is being able to take these representations, add photorealism to them. So you can build a Gaussian splat. Have people heard of Gaussian splats? Gaussian splats are everywhere, or NURFs. And so being able to, you can build just, one of my students, Anthony Opapari. Anthony is a fabulous researcher. He's about to graduate soon. So if you're looking for great people, Anthony is fabulous. But we can build a Gaussian splat of our robotics building just like that. One student can do that. It looks photorealistic, 3D. You can fly through it. We can establish semantics for it. But even those semantics still cause a number of challenges. So when we want to be able to just use more than just the 3D representation, we need to be able to segment the different parts of the 3D map. So this is work that he's done using ground truth labeling. We're able to segment out what the different aspects, what's a sink, what's a door, what's a table, and understand the form and function of objects at the building scale. And so these are the kind of 3D maps that we'd like to be able to build. We have a lot of respect for the work of my good colleague Luca Carlone. We're still, we're contributing to that. And so I'll talk a little bit about our work in segmentation, because even Luca would say that segmentation, semantic segmentation, still remains a big problem, so you don't have flickering between frames. And then once you're able to segment the world and you start to understand the form and function, then there's the issues of affordances. What kinds of things can we do? What kind of actions can your robot take with a particular object? And can your robot work safely around that object? So, for instance, around people, I should say. For instance, let's say the robot, you've built a great map of your environment, and that robot comes to a table and sees this object, and it's supposed to use that object. How should the robot grab this object to do something with it? Well, to us, it may be obvious, but to the robot, it's like, this is just another object. Should it grasp the handle? Should it grasp the lightsaber part? Who knows, right? And so starting to understand that and being able to connect it to language, so you can start to give good prompts to your robot, so you can direct it in interesting ways. That really is our next challenges for robotics. But in order to do this, I believe we also have to think about robotics in a new way. We have to train students to think about this from the ground up, from a robotics perspective, not just thinking of roboticists as at the graduate level, but as we start to grow and you start to see new possibilities, new frontiers, we should think about this at the undergraduate level, because that's what our new challenges in this new environment are going to have. And so I led the creation of our Michigan robotics major, undergraduate major. They would call me the chief architect of our major. And it really is to define the discipline of robotics through our undergraduate program. And this really gets to what we do as higher education. We train people about the ideas we have today for robotics so that they can use them, put them into practice, and then extend them for new ideas for things that we haven't even thought about in the future. That's what makes higher education special. And from a United States perspective, that's why we invest in higher education. And that's really the biggest thing that we can do. We don't make products, we don't make profit, we don't have to win votes. We just, we train people and help them extend the body of knowledge. So to give a sense of what this looks like for humanoids, this is work that Alphonsus Aldubradu, who's now at Boston Dynamics, did with humanoids. And so this was just a bin packing task. And so this was really the robot just picking up different objects and sort of thinking this is like a grocery store helper that could pick this up and stack things in a little bit of a knapsack. And so this would start to add manipulation, dexterity to our robotic platform. And this is what we did. I mean, it says 2021, but really, 2020, this is sort of the beginnings of putting manipulation with robotics. We tried to extend that to doing sort of a shelf stocking task right now. You can see that there's AR tags there. And so this was really about, how could we use it? And at the time, Alphonsus was interested in mixed integer optimization. And so we had, and it gives you a sense of where we were at the time. We didn't really have perception as integrated, so we have AR tags and QR tags everywhere. The robot kind of, it kind of doesn't have full perception of the shelf, and so it makes a few mistakes here or there. It can work. We can combine mobility and manipulation. We should also note that the robot has to move, and then it stops, and then it manipulates. It does the manipulation action, then it moves again. And so it's not necessarily fluid, but that gives you a sense of where we are in humanoid robots. We're starting to get past that state, but it still is true. We could also do material handling tasks. So this was something that Alphonsus worked on with Jesse Grizzle, which was to be able to use geometric fabrics, which is sort of like a robust control basis, to do various tasks in a reactive kind of way. And so this is sort of like null space compositions of controllers, which is an interesting idea. I'm still not convinced because I like some form of guarantee, some sort of robustness. But I think these are interesting ideas. But it shows where we were at that time. And so what I would argue, though, is in order to take the next step, to get beyond sort of like where we are right now, we have to think about a degree program that can produce lots of people that can think about the emerging needs for robotics as a discipline of itself, not just an interdisciplinary research area, that thinks about both equity and excellence, so we can have a positive impact as we make our intellectual advances and meet these emerging needs in society. And so just a quick plug for this. We started it, the robotics major launched in fall 2022. That was our regular season. The number of majors just shot up. The number of declared students in the degree program. It went from, our tagline was, it went from 0 to 60 in 1.1 semesters for the number of students that are involved. And so now there's, at the time I made this slide, there were over 200 students in our robotics program. Now I think it's much more than that. And we've had a large number of graduates for the last several years. And so there's interest in robotics and what we're doing, and we need that help. If you want to know more about what we did to launch the robotics program, we published on Archive. So all the details of what we had to do in the designer program and what we had to do to get approvals, you can see that on Archive. And as we did this, it really led to sort of 3 big questions that I got as I was leading our robotics major. And so the top 3 questions. Does anybody want to know what the top question I get from students for major? Because it's 9 a.m. I'm not gonna ask you to say, but the top question is, what job can I get with a robotics major? You know, like why should I not do computer science or electrical engineering or something that people understand and employers want? And why should I take a chance on robotics, which people don't really know about? Well, at the time it was really hard because the job market was going down a bit, and so students weren't necessarily finding opportunity. But what happened recently is that it turns out that computer science had produced so many people that now computer science was having trouble placing people into jobs, and they were looking more for AI and looking more for robotics. And so, this starts to get, computer science is never going away. You should don't take this as like, don't major in computer science, but take it as, the skill set is broadened and you don't necessarily, and to have so many students in computer science is not necessarily a great thing. We can broaden out and have new areas. My academic grandfather is Rodney Brooks, and Rod makes a number of great points about why humanoids won't necessarily do all the things that we think that we're going to do. All of my students love to talk about VLAs and all these big deep models that we'll learn. But Rod, I think I share his skepticism on that. But there is going to be ways to make humanoids work. I believe Bayesian inference will be a part of it. Who knows, right? And so we need a large number of people to think about these things. Rod would make the argument in his article, in his post, and I think if you saw the New York Times article that was about him, I think this is sort of his skepticism too, that he would make the argument there was this big hype train, generative AI gets really hyped up, and expectations get really high. Not that generative AI is not worthy. It's a great technology. It's done so much. It's better than we thought it was going to be, but expectations get higher than what it can actually produce. And so then you have this trove of disillusionment, right? That may be where it's heading, and humanoid robotics may rise up, and you're seeing lots of humanoids, but maybe it's going to be overhyped, and then there's going to be this disillusionment. But in order to get past that, to get to where these robotic systems can actually be productive, that's where we need trained, committed people that love robotics, love artificial intelligence. And so to get through that dip right there, we're going to need a great workforce. And so that's really why education is so important to our advancements in research. And so that's why we created the Michigan Robotics major. And really, this major, when we think about what it means to be a roboticist, we started off with the definition of what robotics is as a discipline. And so basically, what robotics is, this is our definition for it. Robotics is the study of embodied intelligence for machines that sense, reason, act, and work with people to improve the quality of life and productivity across society, equitably across society. And so this is our definition of robotics, and hopefully this will catch. Maybe this is what's going to be. We're trying to find that tagline, the same way that physics is about understanding the true nature of the universe. This is kind of our, this is our best attempt at that. It's not as catchy, but I think it works for right now. And so I said that already. Our motivation for this is to, lots of people can study robotics in graduate school. But what we can do is graduate skilled roboticists in 4 years instead of 6 years after they've done undergraduate and graduate school, or 10 years after doing a PhD. And that means we really focus on years 2 and 3. We try to emphasize kinematics, state estimation, and autonomous navigation, kinematics and planning, mechatronics, pull those classes into years 2 and 3. And ignore that bit about about the money. That was from 2018. That's no longer valid. And so, but really, where it comes down, where the rubber hits the road, is what is a valid degree path through your through the major, and that is where you have to make important choices about what's important for training roboticists, for defining what a roboticist is, at least at the undergraduate level. And that comes from our program guide right here. This is our diagram of valid pathways through our major. It looks crazy, and what is all that? So I'll try to decompose it. What it means is in the first year, in addition to taking calculus and physics and a number of and English composition, we also try to allow students to do what we call full spectrum embodied intelligence. They take classes in sensing, reasoning, and acting to close the loop. What that really means is that we start with linear algebra alongside or maybe even before calculus and use it for sensing and control tasks. We teach programming through teaching autonomous navigation, so A star with a little bit of a convoluted multi-layer perceptron, and we have a robot building class. So students work with robots from day one. Then we get to the year 2. We put human-robot interaction and professionalism and professional ethics up front. So this is the class that we take in their second year, and so this is an intro to human-robot systems class. So working with people to develop robots for people is really important. We don't want to push that off to the end. Every major needs computing. They need to take first semester data structures, probability, electronics, mechanics. We can't. Those are things that every engineer, every scientist who's working in this area needs. And then this gets to the core. And so in our core, we try to have a set of classes where they have to really deal with sensing, reasoning, and acting and interaction on the whole. And so we have a number of these classes. I teach the Robot Operating Systems class, which is not just a ROS class. It's about inter-process communication and how you develop software systems for robots. And so, so these are our core 300 level classes. But to understand where this comes from is we took the idea of Brooksian embodied intelligence. So Rod Brooks, again, came up with the idea of a sense, model, plan, act framework. So this is from his seminal paper, Intelligence Without Reason, from 1991. And you're really thinking about the closed loop for how robots actually work and how we describe them. And so this is sort of Brooksian embodied intelligence. If we took that idea and we put it into an actual framework, it sort of looks like this, where we have a closed loop between decision making and your actual system, with perception in between, and people interacting with both the system and the decision making. This is just one way of thinking about it. If we take that loop and then we sort of think about everything that's happening inside of it, and I won't go through all of it, but basically, our system is there. We sense the world. From our sensing, we develop partial observations. We develop a model of the world from partial observations. We use that to make decisions. Decisions then go into controls to generate the forces that go into your system, and then we do it all over and over again. And so this is really how almost all of our robot systems work. If we take those and we put the math that we have that goes along with that, and then we also say, well, certain of these deal with interaction, with autonomous robotics and embodiment or mechatronics. this really starts to give us a scaffold what students need to be a roboticist, what our discipline looks like from a programmatic perspective. If we assign class numbers to each of these, then those become our 300 level courses, and then from those we have prerequisites. So in order to study controls and robot design, you need dynamics. Circuits requires, a robot sensing class may require circuits, linear algebra before doing a lot of the autonomy, probability and statistics and programming before you do interaction tasks. And so this really becomes our 300 level sequence. Then that's what gets put into our robotics major, and then that allows us to bring interesting classes from the graduate level into senior level experiences. And so that's really that's the design of our program. And it's worked really well. Students really like it. They're getting a lot out of it. Employers are starting to see the benefits of having students specifically trained in robotics, even if they don't do robotics. It's been so successful that we have to now maintain a fleet of about 500 robots to teach all of our courses at both the undergraduate and graduate level. And so one thing that we've developed is the MBOT platform. And so there's multiple different ones. In my classes, we use the OmniDrive design, but there's differential drives, inverted pendulum. And so we've gotten the cost for these robots down to about $360 per unit, depending on the cost of Raspberry Pi at the time. And so these robots, so this is the OmniDrive version of the robot that I use in my class. So this has laser range finding on it, can move around. OmniDrive robots, giving a lot of thanks to Peter, who's there. Peter doesn't know how much that he and Manuela had influence on me when thinking about OmniDrive design. But we have like really a low-cost platform that you can have, does full SLAM, so our students do, as sophomores and juniors do full occupancy grid SLAM, and as a bridge into larger explorations into perception. And so these are actually a first semester class, where we teach programming through the lens of our AI through autonomous navigation. And so we have to build and maintain about 500 of those robots. Just a small aside there. So that's really our program. But then we get to the next question that students ask me, which is, so where's my robot? A lot of students, where can I go to work with these robots? And I would tell you that your robot is already here. And so we have different types of robots doing all different types of things. And you can buy these robots right now. But the real question is not necessarily how many robots you have, but what are they doing? And so mobile manipulation, so being able to work to move and have dexterity at the human scale is really important. You can buy these robots right now. So usually I ask, because I'm running short on time, I won't ask you how much these robots cost, unless somebody wants to guess. So that's the Willow Garage PR2 that I had when I was at Brown, the Fetch mobile manipulator when I bought my first purchase here. Anybody know how much these cost? Anybody want to guess? What's that? USD, yeah. What? 500K, I like that, there we go. 500, what was your guess again? 20K, all right. I like that. I like all of those answers. The reality is all of those are right, because it just depends on what time you're thinking about. So I bought my Willow Garage PR2 for $400,000 in 2009. First purchase when I got to Michigan was the Fetch robot. It was about $100,000. If you've seen my talk before, you'd say I would say that if you looked at the first humanoid robot I worked with, which was the NASA Robonaut, and you did our least squares regression from linear algebra, $20,000, right? I think that was my prediction back in 2015 of where you're going to see robots. And that roughly is true, So on one end, you've got Hello Robot, the Stretch, which is about $20,000, a little less than that. And then you have humanoid robots, and you have all sorts of other systems that go on the high end. You're going to see all sorts of heterogeneous robots. But this is just the hardware, And so we've gone, from hardware building small numbers of bespoke robots, all the way out to massive numbers where the economies of scale lower the cost. But when we start to think about the software of these robots, the autonomy, when I was a graduate student, it was all teleoperation, remote control. And that was how most of these robots robots work with head-mounted display and VR and those types of things. Over the last 20, 25 years, we've been able to do things like put that there. We have enough autonomy where we can have a robot go from location A to location B, like an autonomous vehicle or a mobile manipulator. And what we're seeing now is the ability to robots to do a task for you. That's what your LLM or VLA was able to do, is start to say, here's a prompt, I just want you to go fix me breakfast. And it's not just doing one action, it's doing multiple actions in a sequence and reasoning through how to accomplish a goal. And that's really where we're going in terms of robotics. And so this idea of having a robot do a task for you is more than just thinking about that. It's about making the physical world programmable. So the same way that computers made digital information programmable, robotics is going to make the physical world programmable, and we should think about that in those terms. You won't think about, I'm programming this robot, but maybe I could give a command to a fleet of robots to accomplish a task for me at some level. And so, really we want robots to work with our everyday homes. Think about things with the clutter that's in those homes or in those environments, work with objects with different forms and functions, such as for cooking tasks, which are more than just pick and place. And when we're doing that, we want robots to be able we want to be able to take the ideal software stack, is we can take any physically capable robot and have it to perform any task in any reasonable environment. And that, and so you don't think about what the robot is or how you program it or the technical details. You just want something to get done, and that's really what's important. So we've been exploring this through one approach that we've had for learning from demonstration is to do what we call semantic robot programming. And so with this, instead of controlling the robot on its own configuration space, we actually have a demonstrator comes in and just shows the robot, this is what I want you to accomplish in the world. This is how I like my tray set up. And so the robot, we just show some arbitrary tray. And this is from about coming up on like 10 years ago, but it was really our beginnings of thinking about that. And so what we would do is we'd show that to the robot. The robot would perceive that goal state using a combination of neural networks and probabilistic inference, represented as PDDL to store that scene graph. So that when it came to a new scene graph, a new situation, it would be able to represent that scene graph, use task and motion planning to be able to transit the world from that current scene graph to the goal scene. And then be able to, and that's how the robot would work. You could just give it that without giving a language prompt. That's how you express a high-level task. And so what's important in this, like I said, is about 10 years ago, is really about that the robot is, you're not telling the robot to do this action or to do this particular motion in its configuration space. The robot's figuring everything out, and the only thing that you've expressed to the robot sits fluently in your own in your shared 3D world. And so that's what's really important. And so we did semantic robot programming with a number of robots, and so we're going to, so our robot is able to work in a number of different scenes with some constraints, but we're able to have that goal-driven robot. One thing that I sort of hid with this is that, the challenges that we have with perception, and so scene estimation and clutter can be a really big issue. And so for all sorts of reasons, such as occlusion, stacking, off-balance constraints, everything that my kids do to mess up our house, this is what we have here. In general, I would say that what we want to do for perception is not rely on green screens or monocolored objects or isolated objects. So usually when we're showing videos of some great manipulation task, we've isolated the world into particular objects, and the clutter that exists in our usual world is not there, or we use AR tags. We'd like to try to ease those crutches. And so one other thing that my group and I worked on was what we call sequential understanding and scene estimation. So this was trying to combine neural networks for recognition with probabilistic inference, so we can get the best of both worlds, the robustness of probabilistic inference and the speed and recall power of neural networks. And so in this case, we're using this, and the robot is able to detect objects in clutter and sort them into objects that should go in the laundry room and objects that should go elsewhere in the house. If you're American and you saw that the comet went into the bin that should go into the laundry room, that's not right. It should go into the kitchen. But that's not because the robot made a mistake. It's because my students don't do laundry or dishes, and so they made that mistake. Anyway, so the way this worked at the time was that we would use a neural network. So we use RCNN to essentially generate candidates of a potential objects that were in the scene. And then from that, we would enumerate the different possibilities of what object could be there. And we would try to refine that into a physical state estimate, to a reasonable state estimate, using essentially particle filters on each object. And that would give us essentially a reasonable state estimate of the world that we could then use to do grasp planning. And so we used the fabulous Rob Platt handle grasp estimator in order to do that. And so this system worked pretty well for doing manipulation and clutter. And we still use this manipulation pipeline in the lab today. But as we come back and talk about, we want to do more than just grasping. We want to know the affordances on the object. We come back to our lightsaber right here. So what part, robot then approaches this object, right? That is obvious to us, but where should it grasp? And so for us, it's pretty easy to know it should grasp the handle. And so the robot should just be able to know that it shouldn't just grasp on the red part, it should grasp on the handle, because that is a lightsaber. But estimating the semantics can be challenging. So one thing that was led by Anthony Opapari and a number of students, Edmund Tong and Audi Balaji and a number of other contributors, was our oval prompt, oval grasp pipeline. And the idea is to think about task-oriented grasping. So, for instance, if your robot is going to grasp scissors and give them to you, should the robot, grasp the scissors by the handle and then lead with the sharp part to give to you? That'd seem pretty aggressive, because it might feel like it's stabbing you, and that's not great. What you should do is like with the person, grab by the sharp end of the scissors and hand, so that you can give the handle to another person. And that really is based on the semantics that we have for these types of objects. And so what we've done is we've created oval grasp, which essentially will take a language prompt as the input, and then be able to use the combination of an LLM and a VLM with point cloud data, and trained up so that we can actually filter grasps based on the semantics of various objects. And so the details are in our paper, which appeared at ICER this year and is also available on arXiv. But essentially what we did the same way is we essentially had different types of objects, and based on the task, based on the language prompt that we would give, the robot would have to be able to figure out where to grasp so it could achieve a particular task. And so when we do comparisons to other approaches like Grasp GPT and Shaped Grasp, we get better results with our combination of LLMs and VLAs. And those are just our numbers right there. But qualitatively, there's a number of things that we could do with this, and that if you ask the robot, if you have a box and you said, read the barcode, the robot would be able to grasp so that it could actually look at the barcode and it's not occluded. Or if you want to know if it has to read a label, it could actually see the label and make sure that it's not occluded, its grasp isn't occluding that. And so this is just some results that we have right now. So if you ask the robot to peel the banana, it knows that it has to grab the tip of the banana so it can peel all the way down. It can hand that over to a person. If you said hold the teddy bear's hand, so that's a language command, the robot could grasp the hand of the teddy bear and move it over. And so we just have what you'll see in a number of these. And so this is like the knife. If you're going to give the knife over to somebody, you should handle it by the blade, and then leave the handle apparent. This is just another example with the mug, holding it by the handle. And so you can do this directly with language prompts, which is a pretty good thing. The other technical part I wanted to talk about was just segmentation for 3D maps. And so, as I showed before earlier on, in this being able to to do dexterity with humanoids at the building scale means that we can start to build the geometry of these spaces, but we still need to know the form and function of objects so that we can have these affordances like we have the oval grass project. But we've got to segment out, and we've got to be able to know that that object is a particular object. And so segmentation becomes really, really important for our 3D maps. One thing that we've been working on, and so Anthony Opapari has been working on this with a number of good colleagues at Amazon, is doing class agnostic video segmentation. So if you use segment anything models, you know that segmentation is getting really good, but it's not necessarily perfect. And so what we want to be able to do is start to think about how we can develop the best segmentation of Gaussian splats, where we can take a sequence of image frames and then be able to get consistent and non-jittering segmentations throughout time and space. So we would know that that thing is that thing and it stays that thing in the mind of the robot for a long time. So what we had, do I have to click through this? Hopefully I didn't. Oh, I went too far. Let's try this again. So one thing that you'll note is if you use something like segment anything models, and there's other models out there like TubeLink and Video KNet, and we introduced FastSpam, is that one thing you want to do is try to avoid flickering per frame. So you don't want to have your segments jumping frame to frame. And so we introduced in 2024 just a self-prompting model and a large-scale data set that could actually produce pretty good results that also built on fine-tuning, and so we could reduce a little bit of that flickering. But then we saw all the great things that are happening with Gaussian splats. So there's a great body of literature out there, and we asked, can we use the splat representation instead of just doing 2D segmentation? Can we use 3D Gaussian splats in order to improve the consistency of video segmentation? And so what we did was we created FastSam Splat. And so with this, basically, we're taking your segment anything model, combining it with a 3D Gaussian splat model, and then using that to try to reprompt and optimize the quality so that we avoid flickering, and we also create a memory that so that when we come back to an area, we don't have to resegment and potentially get a bad resegmentation. And so when we did FastSam Splat, you can see we get much better stability of our segments. Not perfect, but pretty good. And so we can improve that consistency by combining splats with segment anything models. And so this is just showing a little bit of that. And with everything in research, then there's a new model that comes out. So there's FastSam, SAM2 that comes out, segment anything model 2. And so then we compared using FastSam Splat with segment anything too, and we can get pretty good segmentation that we can get improved segmentation that also performs at not the same frame rate as your regular segment anything model 2. And so this is just showing some things that we have there. But one thing that coming back to self-prompting, if we get a false recognition, so it's same with your loop closure problem. You come to an area, you see it, then you go away somewhere else, and you come back, and then then you come back, and you could potentially introduce a false positive or a false recognition, false negative, because it's not the same as when you saw it before. But you could reprompt the segment anything to model in order to get a better segmentation. And so that's where we have SAM2 Splat, where we basically combine, whenever we want to do these sort of re-recognitions in a particular area, we can come back and re-render and optimize what that should look like given our 3D model. So this creates a explicit memory. And so I missed the slide there. Sorry, I'll have to unhide that slide at a little later point. But essentially, this produces a better model for us. And so this is really the things that we're doing to get semantics and robots working together. There's still a number of challenges that we have in still dealing with transparent objects, still dealing with different types of objects that we'd like to hypothesize and what they look like in different configurations for that clamp that's essentially a nerf-based clamp that's on on a table. And also thinking about multi-robot coordination and heterogeneity. So you're seeing in the corner right there, essentially a multi-robot coordination task where multiple different robots have to get to a particular location and do that without interfering with each other. And so that was a sort of combination of MPC with Stein variational inference in order to produce better multi-robot coordination. Which gets to my last question that I get from students is, how can I work in your lab? I get a lot of those, a lot of emails. I usually come back with a question to them, and I ask them, what's that? Does anybody know what that is? Has anybody seen that before? This is salmon. But you've seen this. You've seen this online. Have you seen this? But it is a salmon. But what is the salmon? What more? Can you provide a better descriptor of what that is? Yeah. Well, actually, this was a very, very cool thing. A few years ago, somebody put into one of the image generators, give a picture of a salmon swimming up a river, swimming down a river, and that's what they got, right? And so even when deep learning is right, it's not always right. So I would make the argument that probabilistic inference is still very much needed, and we want to be able to provide the speed and recall power of neural networks with probabilistic inference. And so, this is really the part. We work a lot with probabilistic inference, so factor graph models. So one thing that Stein variational inference has come up with is a way to start to avoid mode collapse, which can be a problematic case when you have probabilistic inference. And so Stein inference makes sure that you're covering your entire distribution and not collapsing to certain modes where you don't get proper coverage. And so when we're thinking about robot coordination, what we're doing is we're trying to represent each robot as its own node in a probabilistic model that's running its own version of model predictive control, and then being able to coordinate using messages with other robots. So the messages are actually probabilistic messages to ensure that to inform each other's MPC inference, so that we can have better planning that's going to be more fluid. And so this really gets to, can your robot, and this is meant to be a lot safer. So get the nice fluid behavior that you have we have with people or working in crowds, through sort of implicit messaging that we have, and get that get that sort of nice coordination and safety to work with robots. And so that's sort of a probabilistic messaging stream that we do. And so this is and also it means that we have to think about controls a little bit more. So all of us who do perception maybe still need to think about controls. And so this is using just a baseline MPC with a Stein non-parametric belief propagation method. And this is working with real robots. So there's our MBots here again, and they're actually able to coordinate sending real probabilistic messages between each other to get to a goal location. And so they can move around very, very fluidly to get to their goals. And I love the fact that we can run this on relatively cheap hardware. For the sake of time, I'll just assume that robot gets to the right spot. The last thing I'll talk about is just MPC is great, but we can do even better. And this is where Stein actually can be useful for us. So if you're doing MPC and you're using a proposal distribution to generate your rollouts, you assume that's a unimodal distribution, but sometimes it could be a multimodal distribution. And so Stein inference helps us characterize that distribution a little bit better, so we can get improved performance on certain control tasks. So for instance, if we take our cart pole can get to a desired set point a lot faster than just using a baseline MPPI, which is multipath predictive integral control, which is sort of a new non-parametric version of MPC. We've shown that it can work pretty well for arm control, and then for walking tasks where you might have different types of uncertainty with the gait pattern. This is, I think, in just the open gym area. We're able to get more stable control just by doing Stein. Thank you for that. And so, in conclusion, if you want to know more about our degree program, it's online. I hope that you can come to AAAI. We're just across town, so you can do that. You can still come see us. I think there's still time to register if you want to join the 10,000 other people. It really is the largest AI conference. This is a shot of my open review panel just after submissions closed, and that active number of submissions around 28,000. We had to review 28,000 papers. I don't know how we did it, but we did it. And so it really is the largest AI conference, which shows, and we'll say more at the conference. One thing that I also can talk about is just we used a large-scale non-evaluative AI reviewer, and it actually turned out to be much better than we thought and much more cost-effective than we thought. I'm not thinking about the energy damage here, but the energy cost, but like in terms of cost and tokens, we were able to generate pretty good AI reviews, non-evaluative AI reviews for essentially under $1 a paper. And so it was really, really promising. So with that, thank you for listening to me talk about the ways we think about people and ideas for robotics. And just thank you, and I'll acknowledge our sponsors and the great people I've worked with, such as Anthony and many great students across our program. Thank you very much.
So we have time for some questions.
Hello, thank you for the amazing presentation. In the beginning, it was a very nice presentation, looking at from the beginning and how you walked through the entire of, I think, your 25 years of career. Mm-hmm. In the beginning, in your definition of robotics, you mentioned embodied intelligence.
Right.
But I sort of missed that point in the entire presentation that, first of all, how do you see embodied intelligence? And what kind of choices or what kind of practices you have taken in your group to make sure that you achieve that aspect?
For embodied intelligence?
Yes.
So embodied intelligence really is about, it's a very big term, right? And it doesn't necessarily mean that you have to be intelligent in of yourself, right? It's your intelligence combined with your embodiment and its interaction with the world. So if I go back to Rod, one of his most successful products was the Roomba. He created the iRobot Roomba robot vacuum cleaner. Very not smart, right? It's just a well-designed system that can work in mostly any environment, robust in mostly any environment. But the intelligence is relatively minimal because it's meant to be low cost, very cost effective. But you could have, but when that vacuum cleaner came out, there were more vacuum cleaners that were much more, computationally intelligent. They could map out their environment. They could do path planning. They could, very methodically clean. Excuse me. And that's what really, and I think that dichotomy is what distinguishes robotics from, let's say, computer science, in that, that we think about the actual physical embodiment, and we don't have to, and it's not all about computational intelligence. So the building is just as important, the embodiment is just as important as the smarts, and you have to think about how they work together. And that's what we're trying to get our students to think about. And, because it can be very easy to dive into computation and math and theory and think that solves everything, but it may or may not, depending on your robotic system.
How do you incorporate that in your curriculum to teach embodied intelligence?
Oh, I see. Okay, if that's your question. You work with real robots. So you work with real robots, right? That's why the MBOT platform is really important, because sometimes students will say, it worked in simulation, therefore it will work. But then when you actually have to put it on the robot, and you have to understand, well, I can't run, my algorithm doesn't run because I've hit the limits of the Raspberry Pi, or the laser rangefinder can't see through the glass in that way. It's actually working with real systems that gets our students to really understand that. And so I think that's part of the embodied intelligence. That's part of the embodied intelligence part, to have that balance of sort of theory and practice. And then we have other different types of robots. I didn't even show the ball bot that that we do for controls, that my colleague Elliot Rouse put together, the different types of arm projects, the different types of bipedal locomotion projects. So that working with real systems is where the embodied intelligence part becomes really important.
Just one small follow-up.
Yeah.
I think my opinion may be a little bit biased because we have a different definition of embodied intelligence in soft robotics. So I was just trying to sort of find that way, or sort of bring you to that point that how you have two ways of incorporating intelligence, embodied intelligence, when the way you suggested that you interact with the environment with a real robot. Right. And the second way is we have a lot of animals around us, including us. We have a very specific way of interacting. Do you consider that as a motivating factor or contributing factor in your research?
I think that discussion is great, and I think that highlights why robotics is ready to become a discipline. I think I'll ignore some of that and just sort of say I will come back to how physics describes their discipline as the understanding the true nature of the universe. But then, what is understanding, right? And that's why you maybe have you may have classical mechanics, quantum mechanics, string theory, everybody's got different ideas, and you go out and you test empirically, and it gives you a lens for how you see the world, and many different debates about what understanding the true nature of the universe means, right? True nature of the universe. I got to get that right. And so for us to understand what embodied intelligence is as roboticists, that's part of the science of what we do, right? How do we understand intelligence that is embodied, that is truly embodied and physically embodied? And I think that pursuit is what really is going to be one of the hallmarks of robotics as we take these next steps into really being a discipline that lasts for decades and centuries to come. When it comes to answer your question about animals and things like that, I will say my advising style is I try to let students develop ideas on their own, and we have interesting debates, and I think there's even within my group of, when, let's say I have N students, I probably have, N squared number of opinions about what embodied intelligence is and how things take place. In fact, we have lots of discussions about deep learning. Are our brains, is deep learning going to be able to mimic human level intelligence? Are we just correlations from data and experience? Or is there something special about us as people? And we have vigorous debates about that. And I think that's why being part of this discipline is really interesting right now. And so love to have that debate with you offline as well. Thank you.
Unfortunately, we've run out of time.
Yes.
But thanks, Chad, for taking the time out and being here as distinguished speaker for the NUS Robotics seminar. So maybe thank you.
Thank you.
For one second.